Hi, Stu Schwartz from MasterMathMentor.com. This is video AB08b, and the topic is the second part of differentiation techniques. It covers the AB manual from pages 34 through 36. While the derivative of a sum is the sum of the derivatives, the same thing does not hold when we talk about products. The derivative of a product is not the product of a derivative. So we introduce the product rule, which says that the derivative of the product of two functions is the first function times the derivative of the second, plus the second function times the derivative of the first. So in terms of notation, we say that the derivative with respect to x of f of x times g of x is f of x times g prime of x plus g of x times f prime of x. Let's look at some examples of the product rule. We start with y equals quantity 2x squared minus 4x times the quantity 3x minus 5. We don't need to apply the product rule here. We can FOIL this expression out, and if we do, we get 6x to the third minus 22x squared plus 20x. And now the derivative is simply the derivative of each term, and we get 18x squared minus 44x plus 20. Now let's see how we can apply the product rule. This is in the form of a product, one expression times another. So the derivative is the first, 2x squared minus 4x, times the derivative of the second, 3, plus the second expression, 3x minus 5, times the derivative of the first, which is 4x minus 4. Now, we still have to multiply this expression out, getting 6x squared minus 12x, plus the result of the FOIL, 12x squared minus 32x plus 20. And putting it together, we get the same answer, 18x squared minus 44x plus 20. Now, looking at the amount of work, it should be obvious that the product rule doesn't save us any time. In fact, it creates some work. So let's see why the product rule is superior in a lot of problems. In B, we're told that f of x equals x squared minus x minus 1 times the quantity x squared plus 2. In this particular problem, we do not want to do the multiplication out. That's 6 different multiplications, and then we have to collect like terms. So we apply the product rule immediately. It's the first expression, x squared minus x minus 1 times the derivative of the second, 2x, plus the second, which is x squared plus 2 times the derivative of the first, 2x minus 1. Now we still have some multiplication to do. We have to multiply the trinomial times the single term and then do a FOIL problem, getting 2x to the third minus 2x squared minus 2x plus 2x to the third minus x squared plus 4x minus 2. Putting it all together, we get f prime of x equals 4x to the third minus 3x squared plus 2x minus 2. Now there's still a considerable amount of work in this problem. In 6c, we have a trinomial times an expression with 5 terms. There is no way we're going to multiply this out. So we simply apply the product rule. The first, 3x squared minus 2x plus 5, times the derivative of the second, negative 20x to the third, plus 6x squared minus 14x plus 1, plus the second, negative 5x to the fourth, plus 2x to the third, minus 7x squared plus x plus 2, times the derivative of the first, which is 6x minus 2. Expressions this complicated are not expanded, so in this case the product rule is far superior than expanding the expression. Your teacher will generally give you his or her rules for expansion. My rules are anything worse than a FOIL problem 2 by 2 should not be multiplied out. While algebra is important in the AP exam, the AP testers do not want to make it into an algebra exam. So problems with a lot of simplification are generally not given, so they can test more the calculus than testing the algebra. Our final basic differentiation rule is called the quotient rule. It states that the derivative of the quotient of two functions is found using this formula. The derivative with respect to x of f of x over g of x is a fraction. Its denominator is g of x squared. Its numerator is g of x times f prime of x minus f of x times g prime of x. So what this states is that to find the derivative of a quotient, we square the denominator. And the numerator is the bottom times the derivative of the top minus the top times the derivative of the bottom. Let's see how the quotient rule works. In A, we're given y equals 5 over 3x minus 2. This is in the form of a quotient. So to take the derivative, the first thing we do is square the bottom. And then the numerator will be the bottom, 3x minus 2, times the derivative of the top, which is 0, minus the top, 5, times the derivative of the bottom, which is simply 3. So our answer is negative 15 over 3x minus 2 quantity squared. In part B, we're given f of x equals 4x minus 3 over 2x plus 1, which is definitely in the form of a quotient. To use the quotient rule, we square the denominator, 2x plus 1 quantity squared, and for the numerator, we use 2x plus 1 times the derivative of the top, which is 4x minus 3, minus the top, 4x minus 3, times the derivative of the bottom, 2. We have to multiply the numerator out and collect like terms, and we're left with 10 over quantity, 2x plus 1 quantity squared. We usually do not multiply out the denominator. In C, we also have a problem in the form of a quotient, negative x over x squared plus 4x minus 2. To take the derivative, we square the bottom, and for the numerator, we get the denominator times the derivative of the top. So it's negative quantity x squared plus 4x minus 2, minus the numerator. So it becomes minus negative x or plus x times the derivative of the bottom, which is 2x plus 4. We will multiply out the numerator and collect like terms, and we're left with x squared plus 2 over quantity x squared plus 4x minus 2 quantity squared. Again, we do not multiply out the denominator. As we have seen, there are sometimes more than one way of taking a derivative. For example, in D, we have y equals 1 over x squared. One thing we can do is we can write this as y equals x to the negative second power and employ the power rule. The negative 2 comes in front, the power reduces by 1, and we're left with negative 2 over x to the third. We can also use the quotient rule. We can square the bottom, getting x to the fourth, and the numerator will be x squared times the derivative of 1, which is 0, minus 1 times the derivative of the denominator, which is 2x. So we're left with negative 2x over x to the fourth, which is negative 2 over x to the third. Probably the quotient rule is maybe just a bit easier here. E also gives us several ways of taking the derivative. One way is using the quotient rule because that's the form of it. We square the bottom, getting x to the fourth, and the numerator is the denominator, x squared, times the derivative of the numerator, which is 2x minus 3, minus the numerator, x squared minus 3x plus 1, times the derivative of the denominator, which is 2x. We need to simplify that. and we get 2x to the third minus 3x squared minus 2x to the third plus 6x squared minus 2x. In this case, the 2x to the thirds cancel, but we're still left with an expression that we can factor. We're going to find that we like factored form, and therefore we get x times the quantity 3x minus 2 over x to the fourth, and that reduces down to 3x minus 2 over x to the third. However, there's another way of attacking this problem. We can write each term in the numerator over x squared. This is called separating, or sometimes splitting it. We end up getting y equals 1 minus 3 over x plus 1 over x squared. And now we can take the derivative of each term. The derivative of 1 is simply 0. The derivative of 3 over x turns out to be 3 over x squared if we consider that to be a power rule problem. And the derivative of 1 over x squared is negative 2 over x to the third. The two answers that we get are not the same, but they are equivalent if we get a common denominator. In this case, probably separation is a little bit easier than the quotient rule. As you work more and more with derivatives, you'll start to get a feel of which technique is best. But do not be afraid of the quotient rule. Sometimes, when something is in the form of a quotient, that's the best rule to use. In a problem like D, we can use the power rule, but we have to spend some time writing it with a negative exponent. And then after we take the derivative, we then have to get rid of the negative exponent. 2 extra steps. The quotient rule eliminates that. So please do not be afraid of the rule. Sometimes you have to use it. So let's put everything that we've learned together. In these 4 problems, you are given a function f of x and a point a f of a. You need to do several things. First, we need to find the derivative f prime of x. We then need to find f prime of a, which is the slope of the tangent line to the curve at x is equal to a. We then need to find the equation of the tangent line to f at the point a f of a. And finally, we need to verify our solution graphically. In A, we're told that f of x equals 3x to the third minus 2x squared minus x plus 2, and our point is 1, 2. We first take the derivative by taking the derivative of each term, and we get 9x squared minus 4x minus 1. F prime of 1, which is the slope of the tangent line at x equals 1, is 4. So using our point slope formula, we have our slope of 4 and our point of 1, 2. Our tangent line is y minus 2 equals 4 quantity x minus 1. And simplifying, we get y equals 4x minus 2. We then graph the function in black and the tangent line in red. And we indeed see that it is the red line is tangent to the black curve at the point 1, 2. In B, we're told that f of x equals x squared minus 4x plus 2 times 4x minus 1. And we want the tangent at the point 1, negative 3. This is a great example where we would use the product rule. And the derivative is the first, x squared minus 4x plus 2 times the derivative of the second, which is 4, plus the second, 4x minus 1 times the derivative of the first, 2x minus 4. Normally here you would be asked to simplify this expression, but since we want the derivative at x is equal to 1, we can simply plug 1 into this expression. And f prime of 1 is 4 times negative 1 plus 3 times negative 2, which is negative 10. So the tangent line is y plus 3 equals negative 10 times the quantity x minus 1 using the point slope formula, or y is equal to negative 10x plus 7. The graph shown seems to verify that the red line is tangent to the black curve at the point 1, -3. In C, we're told that f of x equals 8 over x minus 8 over x squared, and we want the equation of the tangent line at the point -2, -6. We take the derivative using our power rule, and for the first time I've skipped a step or two, getting f prime of x equals -8 over x squared plus 16 over x cubed. The derivative at -2 is simply -2 minus 2, which is -4. So our tangent line is y plus 6 equals -4 times the quantity x plus 2 using point slope formula. And therefore y equals -4x minus 14. Again, the graph seems to verify the solution. In D, we're told that f of x equals x minus 4 over x squared plus 4, and we want the equation of the tangent at the point 2, -1/4. This is clearly the use of the quotient rule. We square the bottom, x squared plus 4 quantity squared, and the numerator is x squared plus 4 times the derivative of x, which is 1, minus x minus 4 times the derivative of the bottom, which is 2x. At this point, we're free to plug in the point 2. I did some minimal simplification here and got 4 plus 8x minus x squared over x squared plus 4 quantity squared. And at this point, we plug in 2, and we end up with 16 over 64, which is 1/4. So the tangent line is y plus 1/4 is equal to 1/4 quantity x minus 2. It is generally sufficient to leave an answer in that form. However, if you wish to graph it, you're going to need to solve for y, which means bringing the 1/4 to the right-hand side. In verifying the answer, notice that the red line is tangent to the curve at the given point 2, -1/4. However, it does cross the curve when x is equal to -1. This is permissible. The equation of the tangent line is only tangent at the given point. In number 9, we are given f of x, but now we'd like to find the equation of the line normal, which means perpendicular to f at the point a, f of a. And again, we'd like to verify our answers graphically. In A, we're given that f of x equals x cubed minus 4x squared, and our point is 3, -9. Our derivative is simple. F prime of x equals 3x squared minus 8x. And therefore, our slope of our tangent, f prime of 3, is 3. We use the fact that the slope of the perpendicular line, or the normal line, is the negative reciprocal of 3, or -1/3. So using point slope formula, our normal line is y plus 9 equals -1/3 times the quantity x minus 3, or simplified, y equals -1/3 x minus 8. Verifying, the function is in black and the normal line is in red. For convenience, I also put the tangent line in green. And indeed, the two lines look perpendicular. Realize that if you do this on your calculator, it's necessary to use a zoom square so that the two axes are equalized. Failure to do that will make the two lines look not perpendicular when indeed they very well may be. In B, we're given that f of x equals -6 over the square root of x plus 1, and our point is 4, -2. We'll use the quotient rule, squaring the bottom, and our numerator is the denominator, square root of x plus 1, times the derivative of our numerator, which is 0, minus -6, which becomes +6, times the derivative of the denominator, which is 1 over 2 square root of x. This is a complex fraction. However, it is probably easier now just to find f prime of 4. And when we plug in 4, we get 6/4 over 9, which is 1/6. So the tangent line has slope 1/6, and therefore the perpendicular has a negative reciprocal of that, which is -6. Therefore, our normal line is y plus 2 equals -6 quantity x minus 4, using our point slope formula, or y equals -6x plus 22. Again, the black graph is the function, the red graph is the perpendicular, and again, the green graph is the tangent line. And again, it seems to verify. In 10, you are asked to find the point or points where the graph of some function f of x has horizontal tangents. The word tangent means slope, and horizontal means slope equals 0. So this problem means that you're going to take the derivative and set it equal to 0. This is something we'll be doing a lot in this course, setting the derivative equal to 0. In 10a, we are given that f of x equals x squared plus 2x minus 24, and we want the horizontal tangent. We take the derivative, 2x plus 2, and set it equal to 0, and we get x equals -1. This is the x value where there's a horizontal tangent. To get the point, we need to plug -1 back into the function. F of -1 is -25. So the point, -1, -25, is the point of horizontal tangency. We verify that on a graph, and the red line shows the line y equals -25, and it indeed looks to be tangent to the curve at the point -1, -25. In 10b, we're given f of x equals x to the 4th minus 4x squared. We take our derivative, 4x to the 3rd minus 8x, and we can factor that into 4x times the quantity x squared minus 2 and set that equal to 0. So either 4x equals 0 and x equals 0, or x squared minus 2 equals 0 and x equals plus or minus the square root of 2. Again, each of those x values have to be plugged in to the function to get the y values. So our points of tangency are 0, 0, square root of 2, -4, and negative square root of 2, -4. 3 points of tangency. You can verify that yourself graphically. I'll leave C to you. In D, f of x equals x minus 1 over x squared plus 3. This is certainly a quotient rule. So to take the derivative, we square the bottom and take the numerator to be x squared plus 3 times the derivative of x, which is 1, minus x minus 1 times the derivative of the denominator, which is 2x. That becomes negative x squared plus 2x plus 3 all over x squared plus 3 quantity squared. To set this equal to 0, all we have to worry about is when the numerator equals 0. And we can factor the numerator into negative quantity x plus 1, x minus 3 equal to 0. So we get two values, x equals -1 and x is equal to 3. Again, we need to plug each of those values back into f of x, and our points of tangency are -1, -1/2, and 3, 1/6. Again, I leave it to you to verify graphically. In video 0607, you learned how to use technology, the graphing calculator, to find the value of the derivative at selected points. On the AP exam, while you may be able to use a calculator, the testers do not want you to use it for this purpose. So they devise another method to determine how well you can take derivatives. This uses a table. So in these problems, we are given a table with the following information. We have a function g, and g of 3 is 4, while g prime of 3 is negative 2. We have another function h, where h of 3 is 3, but h prime of 3 is pi. We are asked to find the derivative of selected functions at x is equal to 3. In A, we are told that f of x equals 4g of x minus 1/2 h of x plus 1. And we're asked for f prime of x. So f prime of x is simply 4g prime of x minus 1/2 h prime of x. The 1 is a constant and its derivative is 0. So now we plug in 3 and we get f prime of 3 equals 4g prime of 3 minus 1/2 h prime of 3. We now look at the table, and g prime of 3 is negative 2 and h prime of 3 is pi, so our answer is negative 8 minus pi over 2. In B, we are told that f of x equals g of x times h of x plus x. So, to take the derivative, we first use our product rule. And f prime of x is g of x times h prime of x plus h of x times g prime of x. And the derivative of x is 1. So again, we plug in 3 now to get f prime of 3 equals g of 3, h prime of 3 plus h of 3, g prime of 3 plus 1. Plugging in, we get 4 pi plus 3 times negative 2 plus 1, and therefore f prime of 3 is 4 pi minus 5. I'll leave C to you. In D, we have f of x equals g of x minus h of x over g of x. We could use the quotient rule, but it's probably easier to separate this. So we get g of x over g of x minus h of x over g of x, and therefore f of x equals 1 minus h of x over g of x. The advantage of this is that taking the derivative of 1 is simply 0. So f prime of x is simply equal to negative the derivative of the quotient, which is g of x over times h prime of x minus h of x times g prime of x over g of x squared. The next step plugs in 3. And now the final step allows us to use the table. And f prime of 3 turns out to be negative quantity 4 pi minus 3 times negative 2 over 4 squared. This gets us to negative quantity 4 pi plus 6 over 16, and we can reduce that down to negative 2 pi minus 3 all over 8. The third derivative can be written as f triple prime of x, or y triple prime, or d cubed y over dx cubed. And if we want to talk about any derivative beyond 3, the nth derivative, we can refer to it as f parentheses n, y parentheses n, or d n y over dx to the n. We will eventually see the uses for these derivatives, but for right now, we're just interested in being able to take them. The second derivative is simply the derivative of the first derivative. In 12D, we're told that f of x equals x over x minus 1. To take the derivative, we'll use the quotient rule. And we get that the first derivative is negative 1 over x squared minus 2x plus 1. To take the second derivative, we have to use the quotient rule again. And we get the denominator squared, and the numerator will be x squared minus 2x plus 1 times the derivative of negative 1, which is 0, then plus 1 times the derivative of the denominator, which is 2x minus 2. And at this point, we can factor out a 2, and doing that allows us to cancel one of the x minus 1's, so our final answer is 2 over x minus 1 quantity cubed. The derivative of a function is sometimes called its first derivative. We say this because there are other higher order derivatives that we can take, the second, the third, etc. The notations for these are f double prime of x for the second derivative, or y double prime, or d squared y over dx squared. For the third derivative, we refer to it as f triple prime of x, or y triple prime, or d cubed y over dx cubed. And for any value of n greater than 3, we could talk about the nth derivative as f n, or y n, or d nth y over dx to the n. We will find later that there are applications for these other derivatives, but for right now we're just concerned about taking them. In the following 4 problems, we're asked to find the second derivative. So in A, we're told that f of x equals 8/3 x cubed minus 5x squared minus 7x minus 1. The first derivative is simply 8x squared minus 10x minus 7. And the second derivative is easily found, 16x minus 10. Although we don't show it, we can find the third derivative, which would be 16, and the fourth derivative, which would be 0, and all subsequent derivatives would also be 0. In B, we're told that f of x equals x squared plus 4x minus 2 all over x. Even though we could use the quotient rule, it's probably easier to separate. So we have f of x equals x plus 4 minus 2 over x. The first derivative is 1 plus 0 plus 2 over x squared. And the second derivative, the derivative of the 1 would be 0, and the derivative of 2x, 2 over x squared, is negative 4 over x to the third. In C, we're told that y is equal to 4 square root of x minus 2 over the square root of x. We write these with fractional exponents and take dy dx to get 2x to the negative 1/2 plus x to the negative 3/2. Note that since we're going to be taking a future derivative, we do not write this with positive exponents. So the second derivative is negative x to the negative 3/2 minus 3/2 x to the negative 5/2. Now we write the second derivative with positive exponents, and we get negative 1 over x to the 3/2 minus 3 over 2x to the 5/2.